Okay, so now we want to study anti-screening of the vacuum. Now, when we studied screening before, this was the subject of classical electrodynamics. And to study anti-screening, we are again going to study a classical theory, but this time we'll be studying a classical Yang-Mills theory. And you'll often also hear people saying a non-abelian gauge theory. Okay, so that's what we're studying now. Now, non-abelian gauge theories are very, very relevant for physics. The strong interaction is described by quantum chromodynamics. That's a non-abelian gauge theory. The weak interactions are also described by a non-abelian gauge theory. Nowadays, with the ADS-CFT correspondence, n is equal to 4 super Yang-Mills is a non-abelian gauge theory. So, this we're studying a theory that is center stage in modern physics. We are going to study, so there's a gauge group which tells us about the symmetry of the theory. We are going to study a theory with an SU2 uh, gauge symmetry. So I'm just going to give you the Lagrangian. We're not going to talk much more about this. Uh, we're just going to study the classical theory. Okay. Now, if you were starting off, okay, so actually the first example of gauge theories, the simplest example is electromagnetism. So let's just review a little bit what we did in electromagnetism. So I think you'll remember that the Lagrangian for electromagnetism is just minus 1/4, and then you have an F mu nu, and you have an F mu nu. F mu nu is called the electromagnetic field strength tensor, and the explicit expression for the field strength is F mu nu is equal to d mu a nu minus d nu a mu. So that was Maxwell's theory of electromagnetism. When we want to go to the SU2 gauge theory, now the field strength gets an extra index. It gets an extra index A. So here is A. And A goes from 1 up to 3. Okay, so we've got three different types of field strengths. And this index A belongs to the gauge fields. Okay, so far it looks like actually we've just added more types of photons. So now we've got three types of photons, three photon fields. Now comes the big change. So there's an extra term that's added here, plus E, that's the coupling strength. We've got an epsilon, A, B, C, and then we've got a B mu, A, C nu. So what does that mean? We've added a nonlinear piece. So this is nonlinear to the field strength. And inside the action, we've got inside the Lagrangian density, we've got the field strength squared. So from this nonlinear piece, you see the field strength has got a piece linear in a piece quadratic in A. So once we square F, we're going to have quadratic in A terms, we'll have cubic in A terms, and we'll have quartic in A terms. So now we're studying a nonlinear theory. This is going to change a lot of the properties as compared to electrodynamics. So, for example, the superposition principle that you had from classical electrodynamics, well, you won't have a superposition principle for a non-abelian gauge theory. Quite apart from that, screening in classical electrodynamics is replaced by anti-screening in the Yang-Mills theory. So that's exactly what we want to study now. Let me maybe just make one comment. So another theory that maybe is relevant for a lot of you that are taking this course is the theory of quantum chromodynamics, QCD. In the case of QCD, the gauge group is not SU2. The gauge symmetry is SU3. And in that case, A would not run from 1 to 3. A would run from 1 up to 8. And these different components of the gauge field would be called the gluons. So you'd get 8 different gluons, okay? But now we're dealing with SU2, so we only have 3 different gauge fields. Good. Okay. Now, when we wanted to study screening in electromagnetism, what did we do? Well, we coupled in a charge. We put a charge in the theory, and then we saw what was the electric field coming from that charge. To add the charge in at the level of the Lagrangian, we would add, in electromagnetism, we would add a current, J mu, and it would couple to the gauge potential, A mu. And J mu in electromagnetism would be a 4-vector. It's a relativistic theory. We would have a charge density, that would be rho, and we would have a current, and that would be J. In the Yang-Mills theory, what happens? Well, we now have a conserved current for each A, so there's a J A mu, and rho A tells us the charge density of the 8th type of charge. So now it's like we've got 3 types of charges and we've got 3 types of currents. If you've got the Lagrangian, you can go ahead and work out the equations of motion. So the equations of motion, as usual, would be the Euler-Lagrange equations. So they would say, let's go back to black. They would say dl dA mu is equal to d nu dl d nu A mu. And if you use the Lagrangian of electromagnetism and worked out the equations of motion that you got from the Lagrangian density with just the black terms, none of the blue additions, you would just get the usual Maxwell equations. So it's often helpful to think back to the form of the Maxwell's equations when you're looking at the non-abelian gauge theory's equations of motion. In the non-abelian gauge theory, we have to modify this slightly. We would add this extra index for the different types of gauge fields that we get. But otherwise, that's exactly where the equation of motion would come from. Now, let me tell you what the equation of motion looks like. You could pause the video and try to derive the equation of motion. I'll just write down what it is over here, and then we'll solve that equation of motion. So the equation of motion takes the following form. It's the divergence of the electric field. So this is exactly what you would have had in Maxwell's theory. Okay, so let's write that. And then this would have been equal to E, the electric charge, and then we would have had the charge density. When we come to modify this in the case of Yang-Mills theory, the first thing that happens is the electric field needs an index A. So there's an electric field for the 8th type of photon, and the charge density also gets an index A. But then that nonlinearity also induces a change. And the change is we've got plus E, and then we've got epsilon A, B, C. We've got a B dotted into E, C. So what you can see is before just the charge density acted as a source for the electric field. So only external charge densities could set up electric fields. Now we see because this photon couples to itself, it's a non-linear theory. And on the right-hand side, we've got some components which don't come from external sources. They are just because now these photons interact with themselves, these different types of photons. So these would be called the gauge bosons. So the gauge bosons interact with each other. And this is the equation of motion that we want to study. We want to study the classical properties of this equation of motion. And the most important consequence of this is going to be that the charge is anti-screened. And we're going to find out that the charge grows large at long distances. So this nonlinear interaction these kinds of interactions tend to make couplings relevant. That's the opposite of electrodynamics, where we saw that screening tends to make couplings decrease at large distances. So electromagnetism tends to make couplings irrelevant. Yang-Mills theory tends to make couplings relevant.